It's my pleasure to introduce my younger colleague of our department, Professor Chandra Volla, who has done his MSc from Central University, Hyderabad in 2005. Then he moved to Switzerland, EPFL, to do his PhD in 2009. And then he did a couple of postdocs. First one about 2.5 years at RWTH Aachen, Germany. And then he moved to Stockholm, Sweden. And in 2014, in October, he joined the department as assistant professor, and he has become associate professor in 2018. And his research interests are mainly on CH activation and organocatalysis related research, metal catalysis. And he has received several awards, mainly the Young Scientist Awards instituted by various funding bodies in the country. He has received all those things. So I just list out few. INSA Medal for Young Scientist in 2018, NASI Young Scientist Platinum Jubilee Award 2018, Alkyl Amines Young Scientist Award 2018, IRCC Early Achiever Award 2017, Theme Chemistry Journal Award 2021, Aura Young Scientist Award 2020, Merck Young Scientist Award 2021, and OPPI Young Scientist Award 2021. So I hope he has grown up now. No? So with this, because I have not seen any Young Scientist Award in 2022. So with this short, brief introduction, I request Professor Volla to give a presentation.
Thank you, Professor Alkan. Thank you, Professor Alkan. And I also would like to thank Professor Ilindatre and Professor Kakkar and the other members of the selection committee for considering our work. And today, to make the talk a bit general, what I decided was to speak about the cobalt-catalyzed CH activation reaction of heliums, which is a theme area in our group. But before that, I want to introduce the three keywords. One is the cobalt catalysis and the CH activation and with heliums. So what is important, so that the importance of our work can be put in perspective. So before doing that, let me also show you the different activities that are ongoing in our laboratory. Basically, we are interested in developing new synthetic transformations based on catalysis. That's our main aim. And along this, we try to explore the enhanced reactivity of a catalytic species and try to exploit its reactivity in general for synthesizing molecules that are of relevance in biology or materials or somewhere. So as I told you, we are working on CH activation reactions. And along with this, we are also using rhodium catalysis to generate a very reactive alpha aminocarbonate from triozoles. More recently, we have been engaged in these two areas where we also use direct group for controlling the regioselectivity of a hydrocarbon or carbofunctionalization and the use of visible light photocatalysis to move into the granular perspective. In this way, we are looking at a metal-free organophotoredox catalysis. And now coming to the CH activation reaction. So as you know that the carbon hydrogen are the two main constituents of all organic compounds. So they exist from a simple molecule like methane to more complex organic molecules or even to the polymers. So it's natural that if you convert the CH bond selectively into something that is useful is introduce a new functional group in case of R, okay, that will be attractive. But there are two main challenges in this case. One is the lack of reactivity. The CH bonds are much less reactive. So in order to activate them compared to activated functional group transformation substrates, you need to use some kind of metal to activate this kind of bonds. And the second one is, while they are ubiquitous, they are present in many different sites. The key challenge is now how do you control the regioselectivity. So for example, in case of a monoarene, if you want to introduce a functional group, typically you will end up with a regioisomeric mixture of compounds. So both these issues can be addressed by a single shot. This can be dealt with using a metal along with a directing group. The ingenious way is that the directing group is typically a functional group of nitrogen, oxygen, sulfur, that is a lone pair, that will coordinate with the metal and in turn brings the metal in close proximity to the bond, CH bond, that is of our interest. At the same time, the coordination of the directing group with the metal makes this CH bond much easier to activate it. At the end, you will introduce the functional group. This kind of CH activation, like many other fields in catalysis, has been really dominated by noble metals which are expensive or scarce. So like palladium, rhodium and ruthenium. But with the growing interest of sustainability, so recently the sustainability theme has gained a lot of importance because to transfer technology from lab bench scale to process, people are looking for more sustainable transformations, and in this case, an ideal sustainable transformation eliminates materials which are scarce and also avoids the use of materials which by their disposal creates environmental concerns. So, with this aim, people are looking for more available, let us say more abundant and also inexpensive transition metals. So, with this aim, we are looking for cobalt catalysis with the aspects of commercial, of course cheaper and much less toxic. At the same time, look at the electronic properties of cobalt. Compared to its congeners like rhodium and iridium, cobalt has a lower electronegativity, small ionic radius. We also want to explore its complementary nature. So, now coming back to the second aspect of allenes in my title, if you see that the most common coupling partners in many organic reactions are the alkenes. As you move from left to right, from alkenes to alkynes to allenes, the selectivity issues keep growing. So, the allenes, which are textbook examples for stereochemistry, if you know that the two pi bonds are in orthogonal planes, this causes some kind of a selectivity issues, and if I list out them, they selectivity issues are known as regio, stereo, chem and positional selectivity. If you want to make it in a much easier way, but slide looks a bit daunting, but I made it slightly less complicated by removing one of the R groups. In case of a monosubstituted allene, I am speaking about an insertion with an organometallic. How many possibilities are there? It's simple mathematics. For each alkene, there is a 1,2 or 2,1 insertion. That's two options, and that can happen from the top face of an alkene or a bottom face of an alkene. So, it adds to 4 options. Since allene has 2 such double bonds with their cumulated, there are totally 8 options in this case. And this is the challenge. At the same time, what we felt that this challenge provides an opportunity to explore the synthetic potential of allenes to construct the molecular complexity. And the story does not stop here, because all these 8 intermediates are highly reactive, and one has to control their reactivity in terms of catalytic cycle. So, the termination step is also a key reaction. So, in order to explore the use of allenes in any catalysis in general, so one has to control the migratory insertion. So, only one pathway will be allowed. At the same time, one also has to modulate the reactivity in the next steps. So, with this idea of the potential of allene chemistry and the importance of cobalt, what we thought was to develop a general cobalt-catalyzed CH activation reaction, that too employing allenes. This is our, we have been working in 2015 since then. So, after a lot of optimization, these are final results where we showed that indeed a cobalt ECAC, which is a commercially available, which one can buy in kilogram scale, can be used as a catalyst to activate this ortho CH bond of benzamides using a Q which is a directing group. The reaction can be done at room temperature and under aerobic atmosphere. So, this is a very operationally simple transformation. What I want you to look at is the product where the nitrogen is connected to the allene part, where is a phenyl group is there. So, this proceeds through an intermediate which we will call a cobalt allyl complex. Now, what is fascinating was that not only it's inexpensive, at the same time compared to cobalt's congener, which is a rhodium, it offers a complementary reactivity. If you see that under very similar substrate classes like another benzamide with a phenylalanine, the reaction is completely complementary. The nitrogen cyclizes at the most sterically hindered terminus in cobalt, whereas the less sterically hindered terminus. This is the one interesting point. And even astonishing was that one can play around with the electronics of the allene substituent, like instead of phenyl, if you have a phosphine oxide, you can completely change the reactivity pattern. Instead of a dihydroquinolenones, you can end up with the quinolinone derivatives. And if you notice that these two intermediates are structurally different. One where the cobalt is connected to sp3 carbon, and whereas the cobalt is connected to sp2 carbon. We try to understand this divergence in reactivity and came up with this proposal where in case of a phenylalanine, the cobalt always likes to stay at the end, either the R terminus or the carbon terminus, and the two such kind of intermediates are possible. Whereas in case of a electron withdrawing olefin, compared to this substituted olefin, this unsubstituted olefin becomes a little more electron rich. So, now the reaction happens on the less substituted olefin. Good. So, this is the origin, what we believe is the reason for this nature of cobalt sigma alkyl versus cobalt alkyl depending upon the substituent. Another question which we asked ourselves is that does it to do anything with the insertion, or these intermediates are precisely formed, or they are undergoing some isomerization. At the end of the isomerization, does the new nitrogen nucleophile react at this terminus? To understand this, we also tried to do some slight modification of the allene and used is derivative which is known as a methylene cyclopropane. And those of you know that cyclopropane exerts a lot of ring strain. So, the moment anything it sees something to isomerize, it will try to open up. So, with this, if there is a no isomerization, if the insertion is guided the pathway, then you would end up with a cyclopropane retaining product. If not, if the isomerization is fast, you will end up with a cyclopropane ring opening. And essentially, we try to test this concept in lab scale, and we found that indeed the reaction happens with the substituted alkene selectively, and it does not undergo any isomerization. The reductive elimination, what we call the nitrogen carbon combination, happens much faster. It is an acceleration of the reductive elimination before the isomerization that leads us to spirocyclopropane derivatives. And we continuing with this interest, we also try to see other directing groups in this cobalt-catalyzed CH activation reaction with allenes. And interestingly, in the case of a directing group, previously I have shown a benzamide substrate and the subtle change from a benzamide to hydrazone. In this case also, we expected that the reaction goes through a 7-membered Cobalt cycle, and if we follow the earlier reaction, we expected the nitrogen carbon reductive elimination give you this 4+2 annihilation product. Interestingly, what happened is that instead of a 4+2, we end up with a 3+2 cycloaddition. So, the cobalt cyclo intermediate, being a nucleophilic, adds on to this imine, which is an electrophilic emitter. Not only does that in an alternative pathway, it does it so selectively that stereoselectively only one product is obtained. In case of two stereocenters, you would ideally expect two different combinations of racemic products, but we obtained only one. So, that shows that the R group and the diazo are in one phase. So, we try to explain the selective formation of this product by this rigid, structurally rigid cyclic 6-membered cyclic transitate, where the cobalt coordinates to nitrogen and the R prime group is in the axial site. So, in this way at the end we will be able to get only one product. We also tested the general of this process. It found to be quite generous at 70 degrees Celsius under aerobic atmosphere as the oxidant. So, it is a aerial oxidation reaction that is taking place at 70 degrees Celsius. And now you see that these transformation also can be very general and can be used for transformations that are having a biologically relevant hydrogen derivatives like epocyanine to morpholin. Different kind of heterocycles are the drugs which are important, can be incorporated in the final indent skeleton. So, along with these allenes and methylene cyclopropanes, we have also been involved in the development of other cobalt-catalyzed CH activation reaction with various, let us say, underexplored coupling partners like norbornines, dienes and propagyric alcohols to achieve some of these transformations which we have been working over the years. So, more recently we have been also involved in developing a new catalytic diannihilation reactions where the allene is used as a linchpin for the diene. So, how do we want to achieve this? We want to use some allene having an X which is a leaving group with after the migrate insertion undergoes reductive elimination of the beta halo elimination, beta oxy elimination gives us the diene product. So, this is interesting because there is very few methods in literature are known for the inserting of diene functionality into an organic molecule. So, we tried to explore this concept using N oxides, and we, after a lot of optimization, I will show you the end result where we showed that indeed that can be possible. The selective C8 functionalization of N oxide can be done with allenes with a cobalt catalyst and negative sodium fluoride. This concept can also be expanded to various substrate classes involving drugs and to multifunctionalized N oxides. So, I will stop in the interest of time, I will not show this one. So, this diannihilation chemistry we have been over the years also developed in a different kind of other transformation as a case study. So, all this have not been possible without these people. I am very fortunate to have these bright and young people, and some of them are sitting in audience. So, thank you very much. I am also would like to thank IIT Bombay and SCRB and DST for their continuous support. I will be happy to take up any questions.